Have you ever wondered how can we use data science tools to improve our understanding of energy systems, contributing to increase their affordability, accessibility, cleanliness, and reliability? The objective of my research work as an inaugural member of the Energy Data Analytics Fellowship was to evaluate how to cost-effectively deploy storage so that it supports utility-scale photovoltaics. By utility-scale photovoltaics, I refer to solar panels with capacities over 5 megawatts, and by storage, to lithium-ion batteries. Similarly, by cost-effective, I mean achieving the maximum reduction of carbon emissions using the least amount of resources. The research question was evaluated using the case study of the Duke Energy Carolinas and Duke Energy Progress service region, operated by Duke Energy. Our selection of this area was based on 3 features. First, the service region provides an advantageous political setting for the development of solar projects. Second, a significant increase in the installation of solar resources in the 2 states highlight the potential for further growth. Third, a substantial amount of the existing power generation capacity in the service region has low operational flexibility, limiting the amount of renewable resources that could be integrated. To identify cost-effective deployment of PV plus storage, we analyzed 135 configurations by exploring 5 PV capacities, 9 levels of storage, and 3 different types of batteries. This was complemented with 5 configurations with just PV and 1 baseline where we modeled the system without any PV or storage, for a total of 141 configurations. We designed and programmed a production cost model comprised by 8 modules, implemented on 3 different computational languages and software. This allows us to simulate the process in which electricity is generated in the DEC/DEP region, following a unit commitment and economic dispatch process. By simulating each of the 141 configurations for an entire year, we were able to examine the impact of PV and storage over key performance indicators of the system. Results from our analysis yielded interesting findings for 5 questions. What would be the expected reduction in carbon emissions? How much does it cost to abate them? What type of storage yields better results? What is the impact over the price of electricity? Can savings from increased use of renewable resources equate the necessary investments for PV and storage? Join me to explore some of our findings. For an extended version of these results, I invite you to consult the paper published in the Applied Energy Journal. By analyzing the results of the different capacities and type of storage, we found that by adding batteries, we could lower the abatement cost while increasing the amount of carbon emissions that were reduced. Hence, we were able to identify cost-effective configurations for each of the PV capacities we modeled. In the same way, we identified a better performance of batteries of short duration for lower PV penetrations, while seeing how batteries of longer duration perform better with higher PV ones. You can note on the figure that batteries depicted on blue yield a lower abatement cost on the left side of the figure, but a higher one on the right side. When examining the results of PV and storage configuration with the lowest cost of abatement, we identified that their installation would reduce carbon emissions by up to 57%. This as a result of an increased integration of PV avoiding curtailment and an increased participation of hydroelectricity replacing fossil fuels. An observation of the performance of the 141 configurations examined in the study shows that while increased storage capacity unequivocally reduces the system's operational cost and carbon emissions, the capital cost of this technology does not justify installation where its power capacity exceeds 25% of the PV installed capacity. Finally, we found that the projection of declining costs for the next decade materialize, the installation of up to 15 gigawatts of PV plus 8.88 gigawatts of 2-hour batteries would reduce the levelized cost of electricity while achieving up to 33% reduction in carbon emissions. We also identified which configurations would reach a break-even point and the different reduction scenarios of both PV and storage. Overall, our results indicate that storage is cost-effective in complementing PV to help a system achieve all its carbon abatement potential, even when this potential is almost fully realized. By using data science and energy modeling, we contribute to building a new future with accessible, affordable, reliable, and clean electricity for our sons and daughters. This work wouldn't be possible without the tremendous support of my advisors, peers, and sponsors. I want to thank you for allowing me to share with you this research, and I hope we can connect and have a broader discussion.